Okay, welcome to the next class on variational methods for computer vision. Today we will continue in a section on convex relaxations part 2. And in this chapter we focus on convex relaxation techniques for a very central computer vision problem, namely that of reconstructing geometry from images. In this section of the chapter, I'll focus on a particular problem, and that is, we saw last time that with using convex relaxation techniques, you can do geometric reconstruction. So given a set of images, typically there's about 20 or 30 images taken from different viewpoints. Given these images, we can construct a photo consistency function, both the classical photo consistency and so-called regional photo consistencies, as I discussed last time, and subsequently we can then minimize this cost function using convex relaxation techniques. And the advantage of these techniques, you see it in this video, is that you can really initialize from an arbitrary surface, and in this setting we use a gradient descent in this example. And you see how the initial surface evolves all the way to the final geometry. And as you can see, one of the advantages is that we don't have to have a guess and an estimate or any idea of what's actually in front of these images. And we saw last time that you can reconstruct essentially arbitrary structures with these approaches. We'll see some more approaches today, but the problem I wanted to start with is the following. Assume that you have reconstructed geometry. So you have the images, you have the geometry, and then of course the question is, what do you do with geometry? Why do you need the model? Maybe you want to put the object into a virtual, say, scene, or into a new scene. You want to, say, take a 3D object that you've acquired in this way and you know, maybe change the illumination, change all sorts of properties, and put it into a new image, say in say a Hollywood type movie. One of the challenges you see is that what we have so far is just the geometry of the object. And as you can see, it's not terribly detailed. The eyes lack detail. The fur, kind of patterning on the fur, is not really there anymore in the reconstruction. But what we can do to recover a lot of these fine details is we can ask, what is the color on this surface? Right? We see an object, but that object has a certain color on the surface. So we can try to reconstruct not just the geometry of the object, but also the color. This is a standard problem in geometric reconstruction or in reconstruction from images. The way this is typically solved is in two ways. One way is that you back project the various textures. And actually this is how it's usually done. You take the images, you back project the color from the images to your 3D geometry, but then you are faced with a certain problem, and that is there is no one image that back projects on the whole surface, of course. So you need to back project multiple images, and then the question is, what do you do with these multiple back projections? And there, the two alternatives that are predominantly used is, the first one is you just take an average of the back projections. And in fact, you can do it a little smarter by what's called a weighted averaging, where you say, well, if a camera is really front-facing, I will put more emphasis on that camera if it projects onto the surface than a camera that sees the same structure from a very oblique angle. And so you would have a weighted averaging of these various back projections, where the weighting depends on how frontal parallel is that view. The second and actually better strategy is, why is this averaging strategy not a good idea? Well, because these back projections are never exactly identical. And once you start averaging, you blur a lot of details. You can imagine that if the geometry reconstruction is not perfect, then the back projection texture doesn't actually end up lying on the exact correct location, and so the different back projections disagree on what the color should be. And if you have many people disagree on something, and then you take the weighted average, you typically get a very blurred decision on what should be the color. A smarter way is that you back project individual textures, and then you figure out on the geometry at which locations do I switch from one back projection to another. When does the back projection change and no longer pick image A but image B to take the color? And that's a stitching problem. It's a very separate optimization problem. It tends to give sharper textures, but the drawback is that if you don't do it well, you see the stitching line. You see where you have the transition from one back projection to another. So how did we end up solving the problem? Differently. That's usually if you see multiple solutions to a problem and you see that all of these solutions have certain shortcomings, that's the time when you decide maybe we should do it better. So here's how we set out to do it, and actually with all that you learned in this class in the back of your minds, you will find this solution is actually the straightforward way to do it. And I must say, when we set out to do it in 2008, 2009, I was actually very puzzled that no one had done it that way before. Here's how we do it. First, you write down what do we have and what are we looking for. We have the geometry, let's call it S, the surface. We have the different RGBD images, so images from an image plane omega I to R3, so there's n such images. And what we're looking for is the color on the surface. What is that? Well, it's a mapping from the surface that assigns to each point on the surface an RGBD value, a color, red, green, blue value, right? So some element in R3. That's what we're looking for. How do we solve the problem? We set up a cost function. And again, for people who don't work in this area, the cost function looks terribly complicated. But for you who've already seen a number of variational methods and approaches in the class, you will immediately recognize elements. You will see what is this here? It's the total variation. The total variation of the color. The only slight difference is that there's a little s in the gradient. Usually the gradient is the spatial derivative operator in x, y, and z. Here it's different. It's the derivative along the surface. So it tells me how does the color change if I move along the surface. And there's 2 degrees of freedom, 2 parameters to parameterize the surface, if you will. And so this is the gradient when moving along the surface. And that gradient norm is integrated over the surface, and so that is the total variation defined for the color on the surface. And it's weighted by a parameter lambda, of course. For some reason, it's always called lambda. Don't ask me why. And what is this here? This is the data term. So that's the regularizer, that's the data term. And basically, to parse these data terms, it's usually a good idea to somehow look at the different components separately. The first thing you observe, there's a square. It's essentially a quadratic data term that we have here. And essentially, if we disregard these 2 elements, it's just t minus I squared. So the color should be the same as the observed color. The color on the surface should match the different colors in the images. For every pixel x in the image, the color at pixel x should be consistent with the color on the surface. The only thing is that, of course, x is defined in the image plane omega I, whereas the color is defined on the surface. Right, so here's the image plane omega I. This is where my little x lives, and this is where II is defined, is the color that you see here, whereas the color I'm looking for is on the surface. And so what I have to do is I have to back project that x back onto the surface. But I can do that because I have the geometry and I know the calibration parameters of my camera, so I can easily do that back projection. I can assign to every pixel the corresponding point on the surface, and the color there should be the same. But now note there is one additional component, and that's this one. It's an operator, a linear operator that I called little b, that models the blurring and the downsampling. And so this is crucial here. I'm not saying the color on the surface should be the same as in the image. I'm saying the color on the surface, once I blur and downsample it, because that's what a digital camera does to the real world. There is a lens that creates a blurring, and there is a digitization into pixels, which is called downsampling. What's essential is this process can be well approximated with a linear operator. The blurring is just a Gaussian convolution, if you will, at least to a good approximation. And the downsampling is simply an averaging over the colors in that pixel area, right? And that's what I model here. And so I'm essentially trying to invert the image degradation process. I'm trying to invert what the digital camera does to the real world. I'm saying the real world is sharp and in focus, and what I'm observing is blurred and downsampled versions of that real world. And so this is what essentially, if you want to give this approach a name, you would call it total variation, de-blurring, de-downsampling, if you want, with multiple images. And this is an approach that's called super resolution. The only novelty is that in terms of the literature, when we published it in 2009, is that this is a super resolution approach defined on the surface S. Of course, this term is defined in the image plane, but you can also convert it to a term defined on the surface. The next thing that you might have seen already is that this expression is actually convex in T. Why? Because the total variation, as you know, is convex. The norm is a convex function. The quadratic penalizer is also convex. It's actually a fairly well-behaved, even convex cost function. And there's some operators in here, but these are linear operators and they don't actually affect the convexity. So the whole thing is convex, which means that we can even compute the provably optimal texture that both minimizes the total variation and or a weighted sum of the total variation and this data term. And so we're saying by minimizing this, finding the global optimum of this cost function, we find a texture that is very sharp and very focused. How do we do it? Well, we compute the Euler-Lagrange equations. This is the Euler-Lagrange equations. We are not going to do this in the exercises. It's a little bit tedious to do it. And in fact, a lot of these terms here actually are shorthand notations. What's maybe interesting, if you look at these shorthand notations, this term here looks a little complicated. What this term represents is exactly the foreshortening that you have with the different images. So the aspect of how frontoparallel is my view. And it basically encodes this foreshortening, and it's exactly the weighting that people had been using in this weighted averaging, in the classical weighted averaging. The good thing here is I don't have to model it explicitly. All I do is set up the cost function, and the rest is standard procedure. And this is important for variational methods, and you see it well in this example. All I do as a modeler is to model on the level of the energies, the cost functions. Once the energy is defined, the rest is standard procedure. Then I can give it to maybe a more skilled engineer and say, here, minimize this energy. And he will compute the Euler-Lagrange equation. The derivative with respect to the texture must be 0, and that's an equation that can be solved using iterative algorithms, Gauss-Seidel type of approaches, essentially. And what you have here, actually, you might recognize it. That is exactly the term that comes from the regularizer. One thing you see is I divided actually by lambda here. So this is not dE by dt, but strictly speaking, dE by dt divided by lambda. So the lambda ends up as 1 over lambda here. So I rescaled everything by lambda. It's not important. You could have the lambda here as well. Same thing. But what you have here is the diffusion component that comes in through the total variation. And since we are not having the quadratic smoothness term, we get this 1 over gradient norm in here. And that is the nonlinear diffusion. If you had a quadratic penalizer, remember that would give us a linear diffusion, and here it gives us a nonlinear diffusion. The idea being that I want to have some regularity of the texture, but I don't want to over penalize discontinuities. So if the colors jump and are discontinuous, this is still acceptable for the total variation. The question then becomes, actually, once you do that, it's a cost function that you ultimately, it's a differential equation acting on the surface. My color is defined on the surface. For example, there are many ways to implement that. One more direct way would be to represent the surface as a mesh with lots of vertices, a triangle mesh, if you will, and then you have color defined on each vertex, or even on each triangle if you want to be more precise. And then you can solve a differential equation on this mesh. An alternative that we reverted to is to parameterize the surface conformally, which means we have the surface here, and then we have a chart, a 2D chart, with a mapping, let's call it, typically it's called phi, that maps from the chart to the surface. And then you can solve the differential equation in the chart. And the advantage is you can just use standard Euclidean discretization approaches and work on the chart. And there are many ways to parameterize surfaces. One way that turns out to be very beneficial in this setting is a so-called conformal parametrization. That is a parametrization of the surface, a mapping from the grid to the surface, which preserves angles. So these level lines, if they have 90-degree angles in the chart, they also have 90-degree angles on the surface. And it turns out then mapping that PDE into a PDE on the chart is actually very easy once the parametrization is conformal. I'll not go into detail here, but you can do it. And then you can take charts, multiple charts, and all these charts, because you don't have one chart representing the whole object, so you're going to have a whole family of charts. This is called an atlas, not surprisingly. Right, an atlas is a family of maps or charts. And so you have all these various maps, phi 1, phi 2, phi 3, etc., to map your whole surface. And then you have PDEs in these various charts that you solve. And the nice thing is you can do a discretization of, say, 2000 by 2000 pixels to get a very high resolution texturing. I'll skip this part. Maybe one comment. We actually extended that then in a later paper and optimized not just the color, but once you improve the color on the surface, you can also update the geometry, because you have images of that colored surface. And once you have a sharper color on the surface, you can say, what if I change the geometry a little bit? Does it make it more consistent with the images? And so that in this setting means that the back projection is updated. This back projection models the back projection to the surface. If the surface changes a little bit, then the beta here changes. And so we can allow perturbations of beta and check which perturbation of beta gives a better color consistency. Right? I want a geometry such that all color back projections are consistent. And I can measure that in the same cost function, and that way improve both the geometry and the color. And what I end up with is a texturing that you see here. So it's a fairly high resolution coloring of the geometry. In fact, the resolution of that texturing is so high that at least I cannot distinguish the virtual object from the real object. I cannot distinguish this coloring from a video of that object. So in that sense, you have a model of the object both in terms of the geometry and in terms of the color on the surface. And once you have that, you could exchange the texture, replace it with a different texture. You can change lighting, illumination, material properties. We'll see examples in just a second. Here's actually the process. Note this is the initial color. If you just back project the colors, this weighted averaging, it's fairly blurred. This is the Beethoven statue. But once I run the super resolution PDE, note how the fine details come out during the iterations. And so you see at some point you can actually read Beethoven there, which was completely lost in the standard coloring scheme with weighted averaging. And so we can recover many fine details in the color by actually modeling it with this super resolution approach. And here is in fact a comparison, this is direct comparison to the state of the art. This is this weighted averaging that people had been doing, and this is the super resolution texturing. That said, you know, anyone who's seen CSI Miami knows that this works. You know, in all these sequences, there's the guy who says, you know, zoom in, and let's say you have a blurred license plate or a blurred image of the killer, and they can always zoom in and get everything sharp. And you know, of course, anyone in this area knows that's not feasible. But it turns out you can actually go beyond the resolution of the individual images. So this is one of the individual images. They all have the same resolution. They all have this pixelization. And this is the coloring that we can compute. And so you see a lot more details than in one image. And at that point, actually, when I saw this result, I thought this is not possible. Over the years watching CSI Miami, I had been telling myself this does not work, this does not work, and now I see it seems to work. But the difference is, of course, in contrast to what CSI Miami people are doing, we have not just one such image, but multiple images. In other words, the same local structure that you see here, you don't see it just in one pixelization, but in lots of slightly differently pixeled images. And in other words, what you measure here in each pixel is an average of the colors in this area. And if you take slightly different averages of the image, you can actually extract a higher resolution picture. That is the key idea behind super resolution. To actually make it work in practice it takes a lot of effort. And I found these total variation based approaches to work better than anything else. At least, let's say, better than anything in that scenario. There are by now more sophisticated super resolution techniques which exploit aspects of self-similarity that say, I want a high resolution picture in a way that the image is in some sense self-similar. And once you have a textural pattern like this, it might actually improve things. But at least in the realm of simple regularizers like total variation, this actually is the best we found. Coming back to 3D reconstruction, one of the things we saw in this first part of this chapter is that in order to get meaningful optima, we had to introduce these regional photoconsistencies. And there was a difficulty in actually defining them. Essentially what we did is we assigned to each voxel a likelihood for the images, given that the voxel is object or given that the voxel is background. But strictly speaking, even if you know that the surface is here, say from a certain image, you don't really know what's behind it. And saying behind it is object is a wild guess. Might be object right after, but if the object is very thin, it could again be background. And so there's a lot of heuristics that entered into these regional photoconsistencies. And so we thought there must be a more elegant solution to avoid this problem of the empty set. So if we go back to this weighted surface area, weighted with the photoconsistency, right? That was saying find a surface that has an overall optimal photoconsistency and a small value of rho when summed over S over the surface. Remember, the problem with that cost function was the empty set is the optimum. And we don't want the empty set as an optimum. And what we can exploit, and this is what we propose to do here, is we know there is an object in the image. We see an object in every image. And so in this approach, we assume that the object we want to reconstruct is compact and has a finite size in some sense. And so we assume that in our image plane, we have the silhouette of the object. We know the object is in this area because we see the object. So we're assuming here that in each image, you can actually outline the boundary of the object. And what does that give you additionally? It gives you what is called silhouette consistency. You can say find a reconstruction in 3D that is consistent with these silhouettes. And so we can impose that silhouette consistency as a hard constraint to the optimization. We can say find a photoconsistent, a maximally photoconsistent surface such that the projection of that surface into image I, so that's this pi I, should be consistent with the silhouette. Let's call it SI, that is this area here. At a first glance, that constraint looks very abstract, and when I first wrote it down, I didn't feel very comfortable about it because I had no idea how would you compute projections of surfaces, how would you impose such constraints. But now it turns out that constraint is actually very trivial if you boil it down to visual rays like shown here. Let's say I have some pixel, let's call it J in the image, I, then I will call this ray here, I would call it Rij, the ray for image I through pixel J here. If that pixel is part of the object area in the image, then what does that tell me? It tells me that along this ray somewhere there is the object. I don't know where along the ray, but I know at least one voxel along this ray must be object. Otherwise, I would not see object there. Whereas if the pixel is not part of the object area, what does it tell me? It tells me that if I walk along this ray, then all voxels in that ray are background. They're not object. Otherwise, if one of them was object, then I would actually see object here. So so these are the two types of constraints that the silhouette consistency boils down to. And it turns out that these constraints are extremely easy to impose because you can impose them as convex constraints. How does that work? Well, we again represent the geometry implicitly by this indicator function. Let's call it U. It assigns values 1 for object and 0 for background. Then the weighted surface area, as you may recall, is the weighted total variation. The total variation measuring the surface area, the area or the number of points where I have a transition from object to background. That's exactly the surface. And then with the weighting rho is the weighted total variation. And these silhouette constraints in this representation can be written like that, where I say if a pixel is part of the silhouette area, SI, then the integral along of U, these binary values, must be at least 1. At least one voxel must be on. I say delta here, but you can just replace it by 1 for simplicity. Whereas if the pixel is not part of the silhouette, then you know that all voxels are 0, and then also the sum or integral of them must be 0. And so these are the two constraints that we have. And what's nice about these constraints is they are linear. This is a sum of u values, and the sum is linear as a function of u, and this is again a sum of u values. One is larger than something, the other one is 0. So it's actually two quite simple constraints. The only aspect that makes it not convex is, of course, this binary representation, but as you recall, what we always do, and this is why the chapter is called convex methods or convex relaxation methods, we drop the binary constraint here. And as a consequence, we get a domain that is functions with values in the interval 0, 1 that fulfill these two types of constraints. They're simple constraints, but of course there's lots of them. There's as many constraints as we have images times the number of pixels. So it's a whole lot of constraints, but it doesn't matter. In optimization, it's not so crucial how many constraints you have and how many variables you have. What's crucial is the problem convex or not? And as I said once before, you would rather want to solve a convex problem with thousands of variables than a non-convex one with 10 variables. Because you'd have to do a complete search in 10 dimensions if you don't know anything about your cost function. And so what you can show, and it's not difficult to show, is that this set of feasible solutions in that relaxed formulation is a convex set. Here, because we dropped the binary constraint, that makes the set convex. And in addition, we have these silhouette consistency constraints, but they are linear. Linear essentially means that in your space of u functions, if that is your space of u functions, you have a set of linear constraints. For example, these inequality constraints essentially mean that you have some hyperplane here, and you say the feasible solutions are on this side of the hyperplane. And then you have another such constraint for another pixel or another image, and that gives you, essentially, you reduce the domain of solutions to those that are silhouette consistent. And what's crucial here is the empty set is not silhouette consistent. And as a consequence, you will never get the empty set in this optimization because that doesn't match the silhouette constraints. And so this is a very elegant way to impose the silhouette consistency in the optimization. To impose the fact that I do see an object in every image. And the consequence is, again, you can then minimize this convex problem. You get a real valued solution, which then needs to be thresholded. So we solve this relaxed problem. Here it is again. And then we threshold the solution by saying, well, the object are those voxels where u is larger than a threshold, and the background are those where u is smaller than some threshold mu. What we lose in this setting is this so-called thresholding theorem. So we can no longer prove that the thresholded version is actually an optimum of the binary problem. But one thing we have is, once we set the threshold appropriately, this looks a little complicated, then we can assure that the reconstruction is perfectly silhouette consistent. What this constraint, what this choice of mu means is essentially you make sure that for every ray that should have an object voxel in it, the threshold is high enough so that at least one of them is on. Right? The problem is, of course, the integral may be larger than 1 here, but once I binarize all mu's, it may be that they're all 0, right? Maybe each of them is just below the threshold mu, then although the integral is consistent with the constraint, the thresholded version is no longer. And so I have to basically select a threshold which is sufficiently small such that for each ray that should be larger than 1 in this constraint, there is at least one voxel that is large enough. And this is essentially what we do here. We show that you can basically take the minimum over all these constraints to make sure that you have a threshold which makes sure that everything is silhouette consistent. And so we get a solution that is binary, that is based on minimizing this photoconsistency weighted surface area, and that is provably silhouette consistent. Beyond that, you lose optimality, but there is a little bit you can show. So although this binary solution we get doesn't give you the provable optimum of the original problem, the silhouette constraint reconstruction problem, we can show that it's within some bound of the optimum. The way this works is as follows. Let's assume the set of binary functions is some non-convex set. I drew this very abstractly, so this is some non-convex set. Then that is the solution, say, we're looking for, some solution that is binary and in that domain, so the minimizer of this energy among the binary functions with the silhouette consistency, of course. We then do a relaxation, meaning we enlarge our set, allowing real values, not just binary, and so we generate the convex hull of our domain. And then we solve the problem in that convex hull. So this would be U star is the minimizer of the relaxed problem. So this domain is larger than sigma binary, and it contains sigma binary. And then we threshold that solution, and thresholding essentially means we find a function, U tilde let's call it, that is then our solution to the problem, which is binary but close to U star. So we find some function that is close to U star but still binary. This is what we do by thresholding. And now you see that U tilde and U prime are not necessarily the same. In general, this is where you kind of lose optimality, that getting from the solution of the relaxed problem back to imposing the original constraint, the binarity constraint, you kind of disregard the cost function in that step. And so you find something that is binary, but is not necessarily the optimum. But in terms of energy, what do we have? Well, the lowest energy, provably lowest, is that of U star. Why? Because we're minimizing energy E in a very large domain. In a domain that contains the binaries among other, but it contains more functions. And so if you optimize a cost function, minimize a cost function over a domain that includes the original but is larger, then your energy is at least as low as in the binaries, right? And so the optimal binary function will typically have a higher energy. It will be above here somewhere. Because this is the optimum among the binaries, whereas this is the optimum among all conceivable functions, even non-binary functions. And now with thresholding, we get an energy of some binary function. Not necessarily the best binary function. This is the best binary function by definition. This is the energy of some binary function, so invariably we're again higher here. But now you see what we can do is we can compute this gap. We can compute how much did our energy change in the thresholding. And we know that the optimum, this one here, is somewhere in between the relaxed energy and the thresholded energy. And so you could write an inequality if you want out of this, basically saying that the gap here between what I did compute as a binary solution after thresholding here and what I wanted originally, this gap here is smaller or equal to, so this gap is smaller or equal to this gap. That's the difference between the thresholded and the relaxed one, and I can compute that energy gap. And so in practice, we lose optimality, but we can compute an energy gap that tells us how bad is our solution. And in many of these scenarios, for example, also in the multi-region segmentation, we find that these gaps are very small, 5% or so. And sometimes, if you can show that after thresholding, my solution has the same energy as before thresholding, what does it tell you? It tells you that you have the optimum. If this energy is no higher than that energy, it basically means I have the best binary solution that I can get. And so this is the nice thing about these convex relaxation techniques that we see here, namely that that you don't get provable optimality, but you get an approach that is independent of initialization, because I minimize a convex problem and then threshold. And secondly, the solutions are within a computable bound of the optimum, and so I can, once I computed the solution, I can say how bad is that with respect to the best conceivable one. Yes?
Is it somehow possible to obtain like the best binarization, or is it possible the best binarization?
That's a good question. So actually a lot of researchers spend time in figuring out what is the smartest way to binarize. And once you look at it more extensively, you find this plain thresholding is actually not the smartest solution. To give you a little more insight, what might be a better strategy, let's say we have a let's say here is our non-convex domain, sigma the binaries, then here is the, once we construct the convex hull of this, we have this larger domain, right? And then I was saying we are interested in this u prime, here's my u star, and then I just find the nearest binary one, u tilde by thresholding. But what if I knew, I mean, I have the cost function and I'm not using the cost function in this binarization. What if I knew, so this is the global minimum, maybe the cost function has level lines of this type, right? What I should be doing is I should be minimizing along the level lines. So I should take, in the binarization, there are strategies to take into account the structure of the cost function, right? To maybe figure out, because then I see this point has a much higher energy than that point, right? And so ideally I would rather try to binarize along the principal axis of this, say, parabola that I fit here. So there are many strategies to improve the solution and to, say, in the binarization try to take into account a certain aspect of the cost function. But the optimal binarization strategy, you're not going to find it, because typically all of these problems are NP hard. And if there was a provably best binarization strategy, one that actually gives you the optimal solution, then you would be solving an NP hard problem here. So there's only so much that you can gain. And as a consequence, people have been proposing a number of binarization strategies, always showing, oh, look, in this example I get a better solution, and in that example I get a better solution. But it's very hard to make more rigorous statements. For example, it's very hard also to say what is this gap before actually computing it. This kind of gap in the community is sometimes called an a posteriori gap. You can compute how far you are only once you solve the problem. But typically, if you want to give performance guarantees to an algorithm, you want to be able to tell, even without the image data coming in, you want to say, how bad is my solution going to be? And this is called an a priori bound, and there are certain bounds that can be computed for these types of problems, but they're typically very bad, if at all. Some of these bounds will tell you you're at worst a factor of 2 away from the optimum, which in terms of percentage it would mean 100% error. That's very high compared to, say, 5% gaps, right? And so there are a priori bounds. They're very difficult to prove, and many times they're not very tight. And so one of the challenges in convex optimization and in convex relaxation techniques is to find a convex formulation that is tight, in the sense that the relaxed solution is as close as possible to the best binary solution. Here are some examples. So this is actually the photoconsistency scheme that I showed in the first section, applied to an object which admittedly violates a number of our assumptions. It is a metallic object, so it's definitely not Lambertian. So the color depends on the viewpoint. In fact, you see there's very prominent specularities, reflections of the lighting that move once you move with the camera. And so that actually creates very nasty artifacts in the reconstruction. The second thing is that since we do a minimal surface approach, typically thin, elongated structures, such as the pedestal here, they disappear. If you go back to the discussion on Mumford-Cha, remember that was even a statement that was proven in the paper of Köpfler, Morel, and Solimini, that once you minimize with a length constraint or a surface area constraint in 3D, then elongated structures are energetically disfavored and they will be suppressed. That's what you have here. Small structures will be suppressed, elongated structures, and these effects are due to these specularities. Here's the approach with the silhouette consistency. Gives a much nicer reconstruction. It also uses photoconsistency, but in addition it uses silhouette consistency, and it knows that there should be object along these rays, so even fine scale structures such as this one will be preserved in the reconstruction. And here's another example, a very untextured object. This is a little pig that we put in this camera dome to take pictures of. We chose this pig because it has no texture. It's just pink. And so if you compute photoconsistency, there's not a lot of local structure that you can exploit, essentially none. You can only see, okay, this is object, this is not. Here's the reconstructions that we can compute with this, and you see they look quite plausible. What does the approach do once there is no photoconsistency information? Well, what we're minimizing is this weighted surface area, rho times ds, if integrated over s. That is the energy we're minimizing. If all points have the same color, then what happens is the function rho becomes constant. Everything is a good match, everything matches, everything has the same photoconsistency. So this is constant. The result is, what I end up with is essentially just the surface area itself. So what the algorithm will do in a setting of no photoconsistency information, it will just compute a minimal surface. A minimal surface that is silhouette consistent. And that happens for at least many objects in the real world, happens to be a good prior to assume if I don't know anything, do a minimal surface. Something that has minimal area. And this is what creates nice roundish shapes. Here's another example of a warrior statue, and again you see that fine scale structures like the hammer or the sword are nicely reconstructed in this approach, because we are imposing silhouette consistency. So despite this minimal surface approach, the small scale structures are preserved. And so you can get very nice and accurate reconstructions. This is a project we did with a museum in Bonn. They wanted to virtualize these Greek statues, Niobe statues. They're about more than human high. And so we went to the museum and we took just some 20-25 images with the standard Nikon camera. And here's the reconstructions. And so you can see we get a lot of, the fine scale structures that we get through the photoconsistency. And at the same time, the silhouettes are perfectly preserved. Here's some more examples. So we did a lot of these statues. There's about 17 of these. I'm just showing a couple. And so you see that this approach actually is an essentially unsupervised method to generate very nice, convincing 3D models just from images. Here's another example, and here you see that again, as this is important for geometry reconstructions, the topology of the object, meaning the number of holes, can be any, doesn't matter. If we go back to the things we started with in geometric representations of geometry, if you represent a geometry with a mesh, for example, or a spline surface, it's much harder to create objects that contain holes, etc. And we saw that one of the first methods to allow the creation of holes was the level set method. But the level set approaches are typically not convex, whereas this is based on a convex cost function. At that point, you would say, well, perfect, that works. I would actually say, if your goal was only to get the most accurate geometry, then buy a high-quality laser scanner, because they're better. They give you more, at this point at least, more accurate geometric structure. So we are at a fairly good level of detail, but the accuracy is not yet in the range of what you can get with laser scanners. Moreover, the laser scanner will also work if you have a completely white object. If you have no photo consistency information, you have little that you can get out of color images. The laser will just measure the distance, and it's very accurate. And the drawback of lasers, of course, in many settings are, first of all, lasers are heavy. So for many applications, say putting a laser in a car is possible, but it adds volume, it adds weight, in particular if you want a high accuracy laser. In addition, and for example, if you do what we do a lot, flying quadrocopters, you don't want to put a laser on a quadrocopter. You can do it, people have done it, but has to be a big quadrocopter. There are bigger ones, but if you want to fly indoors, there's so many trade-offs where a laser scanner is not suitable. Second thing is, laser scanners are slower. They typically scan line by line, and so it takes a certain time to scan a structure. If you work in a dynamic environment where your, say, quadrocopter or car is driving around, or where the structures in the scene are moving from one time to the next, then that's not going to work well with the laser. And lasers are far more expensive. This is an important aspect if you want to deploy reconstruction technology to smartphones, etc. Who's ever going to put a laser scanner on a smartphone? Whereas cameras, sure, there's even multiple cameras on smartphones nowadays. Cameras are light, they're small, they're cheap, and still they get huge amount of data, Even a very cheap camera, there's cameras for 10, 20 euros now, around 10 euros that do 100 frames a second. So it's actually quite amazing what technology you can get in the camera domain. And there's one huge advantage, as I said, if the things you're looking at are moving. And this is what we did here. What we did is we sync. So this is data, actually not our data from Grenoble. What they did in Grenoble is they synchronized 16 cameras and filmed an action with 16 cameras. Here you see the various cameras filming the scene. What can we do? We can reconstruct the geometry for every time step. Something that you would never be able to do with a laser scanner. But we can film, even at 60 hertz if we want, and we can reconstruct geometry for each time step separately. Doesn't mean that our algorithm does 60 frames a second. It's not real-time capable. At this point, the reconstruction that we show here, it typically takes 2-3 minutes per time step. So it's a certain time to do this reconstruction, but what you see in all of these examples is that we can recover geometry at a very high level of detail. To the extent, see a rope jumping girl, we can even reconstruct most of the rope here. I was actually surprised that it actually works at this level of detail. And this is important, right? If if you reconstruct this and the rope is no longer there, then that looks weird. Then everyone would say, "What's the girl doing?" So the rope is semantically very important. And so what this leads us to ultimately is something that is nowadays referred to as free viewpoint television. So we can record an action such as this one, and then the user at home can decide afterwards from which viewpoint to look at the action. Right? And this is going to come in the next couple of years, I assure you, that you're going to sit down Sunday night to watch your favorite movie, and you can choose from which viewpoint to look at the action. That's pretty cool, isn't it? I mean, I sometimes think that the public is not even aware of what things are coming. And as I said, what's important is sometimes you don't have photo consistency. This is a good example. That man has essentially black clothes, and they're black everywhere. And so you can try hard, but you're not going to get any meaningful feature points out. You're not going to get any exact correspondence. Nevertheless, you can see we get fairly good reconstructions, because in the absence of photo consistency, our methods boil down to Euclidean minimal surfaces. And so this is a very nice kind of fill-in effect that we get in the absence of textural information. And so you can do, I mean, you're familiar with these ideas. Like one of the first movies that made this really big is the movie Matrix. Who has not seen that movie? Okay, good, everyone. Yeah, I always recommend seeing it for the visual effects. It was very innovative at the time. They had these scenes where they froze the action and the camera panned around. Well, actually, if you go into the details, they were cheating big time. Why? They just filmed the whole sequence with 60 synchronized cameras. And so when they freeze the action and pan around, what they show is they always show you images that one of these cameras acquired. They never have a full 3D model of the action. They didn't compute it. Here we have a 3D model, and what you see right now is a view of the scene where there was no camera. We don't need 60 cameras synchronized. We can use 16 cameras, and we have a model of the geometry. So we can even change illumination, colors, textures, surface properties, things like that. So once you have reconstructed the geometry and the colors, there's just so much you can do with it that you can never do if you just record images and play back the same images. Yes?
The algorithm considers the shadow of the object as part of the object also?
Yes. In these settings, partially. So, because sometimes you see the shadow here, right? For example, where the dog has... the difficulty is this approach, as I mentioned, uses silhouette information. And although this was filmed, as you can see, in a green screen environment, what used to be blue screen is now green screen. Same idea, though. Apparently green screens work better than blue screens. The problem is that we need the silhouette information. And the problem is, even in a green screen environment, extracting an accurate silhouette is not easy. And there's a lot of effort that goes into reliably estimating the silhouette. Why? Because you have 16 cameras filming at 30 hertz or so. So you don't want to manually extract the silhouettes for all of these thousands of images. It's completely beyond, you would spend weeks and weeks manually drawing silhouettes. So you need something that is automatic. And the result is that the silhouettes are not very good. And then our approach uses these silhouettes, and so the accuracy of the reconstruction is limited by how good are the silhouettes. And if the shadow is extracted as part of the silhouette, then it will be in the reconstruction as well. So this is the issue. This is how the shadows enter our approaches through the incorrect silhouettes. And we use the data, the image data and the silhouettes from Grenoble, and the silhouettes are not perfect. They're suboptimal. And so one way to possibly improve that is to, you know, work a little bit on the silhouette extraction. Once you have the silhouette, you can actually do 3D reconstruction even from a single image. This is kind of the other extreme. What I showed you in the last slides was the extreme where we have tons of images, like, you know, 16 cameras filming at 30 hertz. We're completely swamped with images, and we can reconstruct geometry in that setting. And in a case that happens a lot in the human world is that you are just given one image. And still, as a human, you see that one image and you have an idea of what that object looks like in 3D. We set out to try to tackle that problem and say, can we reconstruct geometry from just one image? And you can imagine that is an extremely ill-posed problem, in the sense that, in principle, there are infinitely many geometries that all would give rise to the same picture. And moreover, if you think more about it, the way humans solve this problem is, of course, by reverting to knowledge. They know what the world has, what kinds of objects are they. They know what airplanes typically look like. They recognize this is an airplane, they know airplanes have wings, etc. And so then they can generate a model of the airplane, a 3D model of the airplane in their minds based on that knowledge. This is very hard to reproduce in a machine. There are efforts, there are people who are trying to go in that direction, how to model knowledge, how to exploit knowledge, how to categorize knowledge, how to use it in reconstruction type algorithms. What we thought is, maybe whatever is missing as information, maybe we can use the user to provide us a little bit of additional information. And maybe we can at least create a meaningful guess of the geometry. And so the question is, can we get geometry from one image? And it turns out there's actually tons of algorithms and publications on that problem, on a problem that is typically called single view reconstruction. These approaches, and there is a multitude, exploit a number of cues in the image. One cue is shading information. If you see, for example, a pillar or something that has uniform color but is illuminated from a certain viewpoint, from a certain side, then you see there is a gradient of the color. The color is brighter in the locations where it faces the light, and it gets darker where it faces away from the light. And if assuming that the object itself has one intrinsic color, you can use the brightness to associate an information about the normal vector, to what extent the surface normal points towards the light or away from the light. That's called shape from shading. It works very nicely if your object only has one color and if you have a controlled illumination. It doesn't work well if you have a real-world object that has varying color and if you have very complex illumination. Why? Because if you have equal light coming from everywhere, then you don't have any information about the normal, right? And so to some extent, shape from shading, even to date, it's been worked on since 1981 at least, so for 30, 40 years. In fact, some of the first variational approaches were for the shape from shading problem. Ikeuchi and Horn is a paper from 81, the same Horn as Horn and Schank. They had a variational approach in 81 as well for these types of problems. But even to date, even 30 or 40 years after, it still only works in the studio, in a controlled environment. And it doesn't work for images like that, forget it. Then you have shape from focus, where you assume that you have a lens that blurs the world, and that there is a certain distance where things are in focus, and if they're further away they get blurred, and if they're closer to the camera they get blurred again. That happens in particular if you have a thick lens. And so it depends to what extent your camera is a pinhole camera. The pinhole camera, the kind of more classical camera that is used to explain the image formation process, is such that everything is in focus actually. And so you have a very basically, and you can see that here as well, right? The grass is in focus, the airplane is still fairly in focus, and so you know, the range of sharpness is fairly large. That so whether the shape from focus, what shape from focus does, or shape from defocus, there are slightly differing formulations. What they do is they exploit that property. And they say, if something is in focus, then it should be in that distance. If it's blurred, then it's a little bit away, either further back or closer by. And then you can try to recover the distance of structures based on the amount of blurring. So you measure locally how much blur do I have, and you can thereby determine the distance of things. And that's not so difficult, you know, determining whether something is in focus or not is very much what the autofocus does on your camera. So that can be done quite fast even. Problem is to actually infer a distance from the camera from the blur, amount of blur, is not always working. If you have no texture, for example in the sky or in that part of the airplane here, then you know you cannot tell how far that part is, because at any amount of blurring, any distance, it would be consistent, the blur that I see. And beyond that, as I said, actually for standard cameras there is a whole range of distances that are in focus, and so you cannot really do much. But again, so this works, and it works fairly nicely. I think we saw examples earlier in the class, in this section on inverse problems. But again, it typically works in a more controlled scenario in the studio. A shape from symmetry, again, is something where you can assume that the object has a certain symmetry, and then you can exploit that. But again, that's not going to always work. So what we proposed, we wanted something that works for a lot of real-world images, at least for images of objects that are seen in a side view, and that are, we will see, we assume symmetry again. Symmetry with respect to the image plane, say for this airplane, for example. The way we do it is we use the silhouette information, and actually the formulation, and that's been used in many approaches, but we wanted an approach that is simple and fast and allows an intuitive user interaction. How do we do it? Well, we say find a minimal surface, so that's inspired by this photo consistency weighted surface, except we drop the photo consistency, so just a standard minimal surface in such a way that it contains a certain volume. How much volume it contains, that's something the user specifies. So that's this parameter V0, and in the basic setting, that's the only parameter the user provides. The volume of my object essentially means the average thickness of the object. This is the one information, or the key information, that I lose when seeing an image of an object. It's flattened to the image, so I don't see the extent of the object. And so what we do here is we say, what is the average thickness, what is the volume? And the volume for this binary labeling is basically, we say, the integral of u is that indicator function representing the object, and that is the volume is the number of voxels that are on, and that we specify. And so we have a constrained optimization problem where we say, find a surface that has minimal area, that is consistent with the silhouette, and that has a specified volume. And then we relax the problem, and there's actually, I didn't mention this here, there's a follow-up paper where we show that you can compute an optimum to this problem. It works very nicely for roundish objects because they are minimal surfaces in some way. So this is an image we extract automatically the silhouette, and then we can basically, the analogy to this problem is that we place a balloon inside the silhouette and we blow air into it, right? And so what you get is these blobby kind of reconstructions, and then we take the texture from the image and project it back onto the geometry, and what we can create is novel views of that one object seen from very different vantage points. And what you have here is an almost 90-degree view. So we take the worst case scenario, we only see the front view and we want to see exactly from the side. And what you get is something that looks at least plausible, I would say. It's not guaranteed to be the right reconstruction, etc., but it's at least a plausible reconstruction. And of course for balloons it's simple because the model is essentially that of a balloon even. But even for other objects such as this one, these are the reconstructions visualized from different viewpoints. And what we show here is what happens if the user changes that volume. The approach is very fast. 2010 it was running 1 second. A year or two later we proposed a much better formulation that is in the fractions of a second. And so the reconstruction is computed interactively. And you can sit at the keyboard, we have a demo, and if you hit plus, let's say, it adds 10% volume. And then you see that arch gets a little thicker every time. And you can basically choose how thick you want it. And that way you have an approach to image-based 3D modeling, where the user can interactively, it automatically extracts the silhouette and creates a 3D model, pops out, and you can turn it and see it from different viewpoints. Here's another example. We take just one single image of that teapot, and these are the reconstructions we can generate. And so you see that they're quite plausible reconstructions of an object that we've only seen in one single image. What's that good for? Well, you know that there is technology that allows you to copy-paste objects. This is actually, I should say, joint work with Microsoft in Cambridge. Carsten Rother, who was at Microsoft, it was a project funded by Microsoft. Carsten Rother contributed to this project. He actually put interactive segmentation methods into this Office package of Microsoft. So if you buy the 2010 or more recent versions of Microsoft Office, then you have a tool that allows you to extract components of an image and copy-paste them to other images. And Carsten put that in there. What this approach would allow you to do is not only copy and paste objects, but before pasting them, you can rotate them in 3D. Right? It creates a virtual 3D model, and then rather than copying that same instance of the teapot into another image, I can rotate it before pasting it back in. And what's more, this is the nice thing about geometric reconstruction. Once you have geometry and color, you can do all sorts of things. You can take that teapot and say, what would the same teapot look like if it had different material properties? So you can, for example, take the same image, extract a 3D model, and create all sorts of different, versions of that object that are somewhat, say, aluminum, metallic, varnish, or this is, this is varnish, so very specular, where things reflect in their surface. And so you can get a lot of new objects with new material properties just from one single input image. Here's the example of the airplane. What we do here actually is we added a functionality because these minimal surfaces create rather blobby structures. Sometimes you don't want that. Sometimes the user knows that the wings protrude more than the rest. And you can actually incorporate such knowledge in that balloon model by adding user scribbles, exactly the ones shown here. And what we say is for these scribbles, we want the object to protrude more in these areas. The way we do that is we change that minimal surface area to a weighted minimal surface area, which means in some locations of the image, surface is cheaper than in other locations. To stay in this analogy of the balloon, it means that we have a balloon that has different thickness. And you can imagine if the balloon is thinner in certain location, it will bulge out. And so using that, we can create this bulging out effect, and we can generate these views of the airplane in very short time, interactively from just one image. Here's another example. The bug. Again, we can extract the silhouette, and just using the silhouette and that model, we get these 3D models. So here you see kind of a movie, kind of video rendering of it that shows you a little better what the thing looks like. And you see we get a fairly plausible model of that little bug, again from just one image. But as I said, this assumes side views. Similarly here we have a side view of the bird. If you have an oblique view, it also works, but not as well, because it invariably creates an object that is symmetric to the image plane. Because we don't actually see the back of the object, right? So we have to assume something there. But with that assumption, it actually works fairly well. And there's follow-up papers where we showed that you can generalize and get objects that are not necessarily symmetric by having a little bit of user interaction. So this is all I wanted to say about these convex relaxations for 3D reconstruction, at least for the binary setting. That is a setting where all I want is to label space with object or background. And so the functions U are binary labelings, and then I can compute geometry, I can compute texture on the surface, I can even compute geometry in time and use synchronized videos to reconstruct actions over time. And as you can see, these reconstructions are fairly accurate, so they give you a fairly good level of detail to the extent that we see even the rope of the rope jumping girl, for example. And then I showed you this extreme case of single view reconstruction, where I use similar variational approaches to reconstruct geometry from just one image. We have a little bit of time left, so I added a few slides to show you, say, where the community is heading today. I think this is always interesting for students to see not only what the state of the art is, but also which direction things are moving. The convex relaxations are a very hot topic. There's a lot of researchers working on this. One extension is to go from binary labeling problems, where we assign just 1 and 0 to each point in space, to what's called multi-label optimization. We already saw one such example, and that was the segmentation, not into 2 regions, but into multiple regions. And so many of these problems have the form that you want a function U that assigns to each point in omega a label in some set gamma. And that's some interval, let's say from gamma min to gamma max. And one good example is stereo reconstruction. We haven't actually talked much about stereo reconstruction. It is a classical computer vision problem. You are given 2 images, And it's a problem of geometric reconstruction, but not fully 3D reconstruction, but rather what's often called 2.5D reconstruction. 2.5D is a term that essentially it means that you assign to each point in that domain a distance from the camera. And so that gives you a representation of geometry, right? But, of course, not any geometry can be represented in this way, right? So if I have the image plane here, and I represent the geometry of this type on my domain omega, then I cannot represent geometries that fold around, such as this one, for example, right? Because that means for a point x, I would have multiple depth values here, right? And so this is why this is not called 3D reconstruction, but only 2.5D, because you can only get the depth map, and you cannot represent any kind of geometry. So you only see, in some sense, the closest surface to your viewpoint. But it's as much as you can typically get from two images to reconstruct a height map or depth map. There's different terms for this. And you can represent this function as a labeling, a multi-label problem, where each label encodes some distance from the camera. That's one example of a multi-label problem. Segmentation is another one. The class of cost functions that are often minimized are of this type. And as you remember, variational approaches have a data term and a regularizer. The regularizer, let's say, is a total variation, for example. And the data term is some data term that basically measures how good is a depth u for a pixel x. And the idea is that rho has small values if that distance gives rise to a good color match. You have two images with a certain baseline, and basically the further away they are, the smaller the displacement from one image to the other, right? And if they're very close by, then you have a large disparity, a large offset between the corresponding pixels. And that disparity is the inverse to the depth, essentially, and this is the function u here. And so we can measure the color consistency. So rho is exactly what we called earlier photo consistency. It tells me for that disparity what are the colors that are being put into correspondence. And if the colors match, then rho is small. If they don't match, then it's high. The problem with these cost functions is they're not convex, because u enters the argument here and rho depends on the images. So much like the optical flow, same problem, except this is one-dimensional, right? So stereo is exactly the same as optical flow, except I'm only looking for correspondence in one dimension. I typically rectify the two images so that the corresponding pixel in the other image is along the x-axis. And so I can represent that displacement or disparity with that function u, with a scalar function. So it's the same problem as optical flow type correspondence problems. It's a correspondence problem, but only in 1 degree of freedom. For each pixel, there is only one dimension to go in. And there is one very surprising, at least for me, surprising aspect. Although this is a difficult problem, the correspondence problems in general are difficult. Once you can constrain yourself to a one-dimensional problem where you search only in 1 degree of freedom, it becomes tractable. You can actually compute provably optimal solutions even for this class of non-convex problems. And the way this works is that, and this we showed in 2008, we tackled multi-label problems with these convex relaxation techniques. That's in some sense straightforward. The Chan-Isidoglu-Nikolova paper that proposed these convex relaxations for 2D segmentation, as for two-region segmentation, that was out around 2006, and then the community basically jumped on that and said, how can we improve on this? How can we generalize this to other types of problems? And one such problem is this multi-label problem, minimizing such non-convex energies with a multi-label function u, a real valued function u. The way you can rewrite this, and the idea is now to map this optimization problem back to a binary optimization problem. How do we do that? Well, let's say this is omega, the image plane. Here's the function u we want to find. Finding a function u amounts to a binary labeling of that space. The space represented by omega times the label space. So if, let's say, you're working with the image plane, you consider the image plane and the number of distance values that you want to allow, and so you represent your world as a 3D world. So basically you're adding a dimension to the problem, but what's interesting is that any u can be represented by a function v, a binary function v, and you can show that minimizing this expression with respect to u is equivalent to minimizing this expression with respect to v. The huge difference being that this cost function is convex. Maybe to show you why these two are equivalent, in particular, let's look at the data term. What we have in here is dv by d gamma. Gamma is this, the direction in the label space, this gamma here. dv by d gamma, if we go back to the plot, how does v change in gamma? Well, the function v by construction is 1 below the graph and 0 above the graph. So the derivative in gamma direction is actually 0 most of the time. The only locations in terms of gamma where it's non-zero is exactly where gamma equals u of x. If gamma is u of x, this is where dv by d gamma is non-zero, in a way that dv by d gamma is nothing but delta of gamma minus u of x. And if I use that expression and plug it in here, right, and then I have delta function of gamma minus u of x and integrate over gamma, then the only term that remains is if gamma is u of x. And then you have exactly the cost that you have here. So you're integrating that cost over the whole volume, but what ends up being aggregated is exactly the same cost here. So it's not actually very difficult to see that that term of the cost function reproduces exactly that cost. And similarly, you can show, this is the so-called co-area formula. These are what I called earlier the upper level sets. And if you take the total variations of the upper level sets, it gives you the total variation of u. It's called the co-area formula. And so that way you can show that these two problems are equivalent, except this is a convex cost function. The problem is still non-convex because these functions v are binary functions. But now for this class we can relax the binary problem, and for this class of problems the thresholding theorem can be proven. And so you can prove that if you solve this over real valued functions in the interval 0, 1, sorry, it should be omega times sigma. Sigma is omega times gamma. Okay, that's right. If you solve this for real valued problems and then threshold, you get a global optimum of this binary problem. And that optimal solution is equivalent to the optimum here. And so we can actually solve this stereo problem in a provably optimal way. And so this is one example of a minimization scheme for an image pair where the goal is to compute the disparity or a depth map, and this is the depth map for one of these Middlebury benchmark images. This is a more real-world example where we took two images taken from an airplane of Graz, or at least a part of Graz. And this is the depth reconstruction we computed. And so you can see with this approach, it's a fully automatic approach that is based on just minimizing, computes a global optimum of our correspondence cost function. And you can see the level of detail is sufficiently good to see the chimneys of the roof, the lantern posts, the cars, the roof shapes, everything is there. So it's a fairly high resolution depth map that we can get from airplane images. And so this kind of summarizes the lecture in general. I showed you variational methods. I showed you more recent developments on how to convexify variational methods. And I showed you examples such as this one, where you can solve very challenging real-world problems by phrasing them as a variational problem and by convexifying them in a manner that you can actually compute provably optimal solutions. That's all. Thank you.